AP Chemistry, Hoover High School. This is the answers video to the Day 60 assignment, which was assigned on Tuesday, December the 1st, and that's due on Friday. So let's go ahead and do this. It has to do with resonance and formal charge. So what is resonance? What is a resonance structure, and what is the purpose of formal charge? So those are answered in the instruction video. So watch the instruction video and answer those two questions. Write the formula for formal charge on an atom and explain what it is used for. So let's go ahead and do that because we're going to need to use it for these answers. So here it is. Okay, so the formal charge is the number of valence electrons an atom has in its natural atomic state before it's bonded to anything, minus the number of lone pairs that it has in the chemical bond, then minus half the number of bonding electrons it has in the chemical bond. So this one just applies to the natural atom before it's in any chemical bond. These two apply to its configuration, electron configuration, inside the chemical bond, okay? And we'll discuss it in a little more detail when we actually see an example. All right, so let's go ahead. We're asked to just draw a few Lewis charge structures here. So let's go ahead and do that. So we have silicon tetrafluoride here. All right, so this is what you did in yesterday's assignment. So I'm going to count the number of valence electrons. So there's one silicon atom, and there's come to the periodic table, and there's 4. It's in the same group as carbon, so that's 4 valence electrons. 1, 2, 3, 4. So we're going to put 4 there. And for chlorine. Okay, so there you go. So it's a lot of electrons to deal with. When you ask which is the least electronegative, silicon is to the left of chlorine. Remember, electronegativity increases as you go to the right. Chlorine would be more electronegative than silicon, so silicon is going to be the central atom. And you just assume that the chlorines are spread symmetrically around the silicon. Okay, so that's we've done that. Now we are going to place single bonds between these, and that is 8 electrons. We need to place 32. The next step is create octets around all of the outside or terminal atoms. Okay, and if we count all of those, you're going to count 32. 8, 8, 8, and 8, that's 32. So everything here has an octet. We've used all 32 electrons, so this is the final configuration for silicon tetrachloride. Okay, let's do PF3 here. Okay, so we're going to count valence electrons. Phosphorus right here is the 5th element from the left. 1, 2, 3, 4, 5, so it has 5 valence electrons. All right, so we have to place 26 electrons for this molecule. Phosphorus is least electronegative, or if you go back to our rules, assuming you have those somewhere, you can always pull them up. Fluorine is never a central atom because it is the most electronegative element on the periodic table. So we're going to draw this fairly symmetrically. Placed those there quite yet. You could ask, could you do it at kind of like this at angles? Again, as I mentioned in an earlier problem, you can do that, but we're not worrying about geometry right now. Just everything should be kind of linear, up, down, sideways for right now. Okay, so now we're going to place electrons between the terminal atoms and the central atom. That uses up 6 of the 26. Now we're going to create octets around everything. Okay, and I've created octets around all the fluorines, and we've used 24 electrons. If you count all of those dots, we need to have 2 more, and phosphorus needs 2 more to have a full octet. So the next rule stated that we needed to place lone pairs on the central atom, which we're going to do right there. and that completes the problem. We've used 26 electrons, and all of these atoms have octets. So that's the final answer for this. All right, let's do carbon disulfide. All right, so we're going to count the valence electrons. And sulfur is right here below oxygen, so it also has 6 valence electrons. And that's going to give you 16 valence electrons you've got to account for. Okay, so now we're going to figure out what goes in the center, which is the least electronegative. And it's fairly rare for this to happen, but if we go to the periodic table of electronegativities, we find carbon is 2.5 and sulfur is 2.5. They're both equal. So how do you choose? Well, it's you kind of guess, but you kind of assume that if there's 1 carbon and 2 sulfur atoms, that probably the carbon's going to be in the middle and the sulfurs are going to be on the outside. And then what you could do at the end is you could do a different configuration, a sulfur, and a carbon, and you could check out do the formal charge on that and see which of those 2 configurations is most stable. So that's ultimately how you would do it, but we're going to just assume that the carbon's in the middle. We're going to avoid doing that right now, the formal charge right now. Okay, so we go on back here. So we're going to draw it like this, just as a linear molecule. There we go. And now we're going to put single bonds between the terminal atoms and the central atom. That's 4. We need 16. We're going to complete octets. Okay, there we go. So now we've used 16 electrons. Okay, so that part is good, but carbon does not have an octet. So we don't want to remove any electrons or add any electrons, so the only option for us is to rearrange the electrons so that carbon has an octet. And that's pretty straightforward. We're going to take a couple of outside lone pairs. Okay, that's why you don't want to do this in ink. And you want to put them in here, one of them here, and one of them here. So now sulfur has an octet, carbon has an octet, and this sulfur has an octet. Looks very much like kind of the configuration of CO2. And that's it. That's your final answer. You've met both of the requirements. Again, if you wanted to do this, and when we get into formal charge, I'll show you this. How do you know it wasn't this? Okay, that would fulfill the same rules, and your first reaction might be, well, this one looks lopsided, this one looks balanced, this one looks lopsided. That's not always the case. It's usually a pretty good indicator, but you could actually do what we're going to do, which is called formal charge. We're going to do that later on in this lesson. Right now, we're just drawing Lewis structures. Okay, HOBr. All right, so do this one. Okay, and bromine is right here, 7 valence electrons. Okay, and you add those up, you get 14 electrons. All right, so between oxygen and bromine, what we're going to do is we're going to look at our periodic table of electronegativities, and this likely is going to give us an exception. So oxygen has an electronegativity of 3.5. Bromine has an electronegativity of 2.8. So that would mean bromine should be the central atom. It can't be hydrogen because it never can be a central atom. It should be H, and then a Br, and then an O. So we're going to actually test this one out when we do formal charge. So the question is it this? Which puts the least electronegative element. Let me get back to my screen there. Okay, which puts the least electronegative element in the middle, or should it be this? Because this is the way it's written in the formula. Oftentimes that's an indication of how the atoms are arranged. And the answer to that question will be something that we will learn to determine based on formal charge. Okay? All right, so let's go ahead. I'm going to go ahead and assume it's this one, because that's what the formula says. It may or may not be right. So we're going to put 2 there. We need to deal with 14. Hydrogen has already filled its valence orbital, so we're going to fill this. Okay, so now we've used 10. There's 8 and there's 2. So we need to have 4 more. So what we're going to do is we place them around the central atom. That's what it says to do. Make lone pairs around the central atom. Okay, and there we have 8, 10, 12, 14. So we have the proper number of electrons, and everyone has an octet. We could have done exactly the same thing here. There you go. Everyone has an octet right there. And we'll see, we're going to see in which one of those is the proper configuration. Okay, and BRF5, actually, I'm going to scratch that one. That has to do with an extended octet exception, and you haven't learned about that yet. We'll learn about that when we get back from the next break, so I'll scratch that one for right now. I'm going to leave these to you. This one was done actually in one of the videos. This one we did in the previous assignment. See if you can do it without looking at that answer. And this one is pretty straightforward. Remember, it has that plus sign means it's deficient by 1 electron from what you would count for nitrogen and for hydrogen. So you count the valence electrons, and then you're going to subtract 1 because it's deficient because of that plus sign. All right, so what we're going to do down here is we're going to draw some resonance structures. Resonance structures are pretty much kind of what I drew in that last example that we did. It's pretty much 2 different structures that could be formed from the rules of the covalent, forming covalent bonds. So let's go ahead and count the number of valence electrons. So this we're just going to do oxygen. Has 6 valence electrons. And then we're going to add on this extra electron down here just as an E-. Okay, and you add all that up and you get 9, 15, and 16. Okay, least electronegative element here is going to be carbon. So we're going to pretty much draw this exactly the way we see it there. We're going to put 2 electrons between nitrogen and carbon and 2 between carbon and oxygen. That uses up 4 of our 16. We're going to complete octets around the outside. And how many do we have? We have 8 there. We have 8 there. However, we see that carbon doesn't have an octet. So when you have the correct number of electrons, but not everybody has an octet, you don't want to add or erase any. You just want to rearrange them. And we're going to do it similar to the way we've done it before. We're going to take these lone pairs off of the ends here. You could have taken other lone pairs, but this just makes it more symmetrical. And you're going to put one of them there and one of them there. And so now everyone has an octet. Now, 2 other ways you could have drawn this, and it would have violated one of the rules for making these. That is, the least electronegative goes in the middle. But you could have drawn it like this. Okay, you could have drawn it with the nitrogen in the middle. You could have drawn it with the oxygen in the middle. It would have violated one of the rules, but what we can do with this is we can test to see which one of these is the more stable element. We are there, so let's do that. So what I'm going to do is, let me do this. Let me erase this one just to move it over a little so I can create some space for myself. There we go. Okay, so first we're going to analyze this nitrogen. We're going to do it the same way we did it in the video. So let me draw a line here, break that off. So for nitrogen, it is the 5th element over from the left in its row. There it is right there. So 1, 2, 3, 4, 5. So it starts off with 5 valence electrons. In this configuration, it has 1, 2, 3, 4 lone pair electrons and half of the bonding electrons, which between nitrogen and carbon are 4, so half of 4. Okay, and that's going to equal 5 minus 4 is 1 minus half of 4 is 2, so 5 minus 4 minus 2 is negative 1. Like that. Carbon has 4 valence electrons in its natural state, minus the number of lone pairs it has right here. You don't see any, there's none. Minus half of the bonding electrons. It has 1, 2, 3, 4, 5, 6, 7, 8. All of its electrons are bonded. So half of 8 is 2. Is 4. So 4 minus 0 minus 4 is 0. So that has 0 formal charge. Oxygen. Oxygen in its natural state, again, the first number is always what the atom is in its natural state. So oxygen is 1, 2, 3, 4, 5, 6. Oops, front screen here, 4, 5, 6. 6 valence electrons minus the lone pairs. 1, 2, 3, 4. 4 lone pair electrons minus half of the bonding. 1, 2, 3, 4 bonding. So 6 minus 4 is 2. And half of 4 is 2. So 6 minus 4 minus 2 is 0. Okay? So there's the formal charges. So these two are stable. This one is not quite stable. It has some number other than 0. Now notice something here. Our formal charges don't add up to 0. Negative 1 plus 0 plus 0 is negative 1. And that's because we're dealing with an ion that's a negatively charged ion. It has an extra electron. So whatever the sum of your formal charges is should be the same as whatever the charge is on the atom. Up until now, we've only dealt with, on the molecule. We've only dealt with neutral molecules, but now we have an ion here, negatively charged molecule. And so that means the formal charge is going to show that negative charge when you add the formal charges of these 3 elements together. Okay, so let's see about this one right here. This time we put nitrogen in the middle. Okay. All right, so what we get is for carbon, is we have 4 minus 1, 2, 3, 4 lone pairs minus 1, 2, 3, 4 bonding electrons. So you want half of those. Okay, so 4 minus 4 is 0. Minus half of 4 is 2. And so that's going to be a 4 minus 4 is 0 minus half of those is 2. So 4 minus 4 minus 2 is going to be negative 2. Nitrogen. It has 5. It's the 5th element from the left on the periodic table. Okay, and then it has no lone pairs, so minus 0 and minus 1/2, and all of its electrons, 8 of them, are bonding. So 5 minus 0 minus 4 is going to be 1, positive 1. And finally we have oxygen. 6 valence electrons, minus 1, 2, 3, 4. 4 lone pair, and half of 4 bonding electrons. So minus half of 4. So that's 2. So 6 minus 4 minus 2 equals 0. Okay, and what you'll notice is if you add up the formal charges here, negative 2 plus 1 plus 0, you get negative 1, which again is the charge on the ion. All right, so it would seem that this is the least stable of them because the difference from 0 is greater here than it is here. All right, so that is the answer to, that's how you do this, and that's how you would know that this is really the proper configuration for this. Carbon should go in the middle. And our rule saying that the least electronegative should go in the middle validates that. All right, let's try another one. Okay, so NCS, again, it's a negative ion there. So carbon is less electronegative than nitrogen. What about sulfur? Is it less electronegative than sulfur? Well, let's take a look. And on the periodic table, sulfur's a 2.5, carbon's a 2.5. We saw this before, so they're even. So what we're going to do is we're going to try it both ways. So we're going to, first of all, just count the valence electrons. Let's do that over here. Okay, so nitrogen, there's one of those times 4. Excuse me, times 5. Hope you caught that. Looking ahead to carbon here. Carbon is times 4. And sulfur is right below oxygen, so it has 6, the same as oxygen. And then you have that additional E minus for the ion right there. Just put it like that. So you have 10, 15, 16 valence electrons to deal with here. Okay? So let's try NCS and CNS. And let's try NSC. Let's put the S in the middle. We can follow all the rules except for the one that says the least electronegative should be in the middle by forming any one of these 3 structures. So we have 16, we place 2 there. Octets all around. So now we have 16 electrons, but again, carbon needs to have an octet, so we're going to erase an outside pair there and put them inside. And now everyone has an octet. And you could make that same, if I give myself a little more space here, you can make that same configuration with these other 2 combinations of the elements. By the way, when you draw this, you should put a 1 minus up here, and I should have done that up above. It's indicating that when you draw the Lewis dot that there is a negative charge on that. And for this one, we'll do the same. Okay, and that should have a 1 minus also. Okay, so any one of those 3. So we're going to go ahead. I'm going to do this quietly. It's a good chance to practice. I know it's a lot of math. You've got to do 9 of these equations, and I'll go ahead and do them. It's just a chance to practice them and really kind of get this cemented in. All right, so here we go. I'm going to go ahead and do these. Gin is 5. I'm going to move this down to the bottom because I'm not going to have space over here. So I'm moving it for the second time now. I'm going to go ahead and do this one over here. Okay. And let's do the last one down here on the bottom. I'll just draw a line like that. And that was NSC. That. Okay, there are our formal charges. And the one that comes closest to 0 is this one. The one that's definitely the furthest away is this one. That's the least stable. And this one is somewhere in the middle, but this is the configuration that you would find in nature. Okay, I'm up against my time limit for a video, so I'm going to do the rest. I'm going to do the rest on a different video. I'll go ahead and put that up, and I'll go ahead and post this one, and you can get going on this assignment. All right, have a good day. I'll see you on the next video.